Thank you very much. It's a pleasure to be here. So as Ayelet said, I work at the intersection of geometry, physics, and computation. And some of the projects I do involve mesh processing and geometry processing, but I thought I would specifically focus today on simulation of physical phenomena, on computing motion. And why am I going to look at that? Well, I want to kind of convince you that there's really interesting geometry that takes place when you're computing motion. So let's dive in. This is my first computation of motion. This takes place in about 4000 BC. And it is a painting on a wall of a cave in Spain. And you could think of it as a painting of an 8-legged boar, or maybe the artist was trying to depict motion in the best way that they had available at the time. And of course, our interest in depicting motion has evolved since then. And as Ayelet said, one of the studios that we've worked with is Disney Studios, which is known for a lot of their classical animation work. And one of the things that I find fascinating is the process by which artists are taught to animate physics. And the idea is somehow to depict emotion or intention or storytelling while preserving physicality. So here is the classical sack of flour exercise, which is an exercise that's been used to train animators since the early days of Disney. And the idea is to draw a sack of flour that is sleepy or happy or depressed or sad, but it still clearly looks like a sack of flour. And even today, animators go through this exercise. So when we're computing motion, we want to ask ourselves, what's the analogy to the sack of flour exercise? You know, how do we model the qualitative aspects of a physical system while still allowing room for storytelling? And there are lots of perspectives on how to do this: human perception, human-computer interaction, lots of different things that come into play. The one I want to talk about today that ties into the theme that we've seen recurring in this conference is geometry. Follow the geometry. And so maybe in today's talk, I hope to give you a sense of what I mean by following the geometry. So here's my first example. This is the motion of the planets around the sun. And you can write down gravitational force. It's an inverse square law. And you can write down a second order ODE, F equals ma. And you can carry out a classical integration. But there's also a geometric view for the motion of the planets around the sun, and that's Kepler's second law. And so if here is the sun, and the planet has an orbit that's elliptical, then Kepler said if you look at the planet at any instant, you have a radius from the sun to the planet, and you take out your watch and you measure some interval in time, and the planet will trace out some pizza wedge. And if you do this at another instant in time, and you measure the same duration, the same elapsed time, you'll get a different shaped pizza wedge. And Kepler's second law is that the pizza wedges will have the same area. That's a description of the orbit. So it means that when the planet is close to the sun, it has to be moving fast. So you get a short, fat pizza wedge. And when the planet is far from the sun, it moves slower to make a skinnier pizza wedge. It characterizes the speed of the motion. Now, where is the original proof of Kepler's second law? Anybody? Anybody? Newton. That's right. So if you, I will talk about that in a sec. So what I want to say here is that this connection between physics and geometry has been studied for centuries. I think what's new in the past maybe 10, 20 years is how does computation enter into this connection? How does the connection between geometry and physics enable us to make better computations of physical systems? So here's Newton's Principia, and the page in the Principia actually shows a discrete argument for proving Kepler's second law. Here's the sun. This should have a pointer on it. And the motion of the planet follows a piecewise linear trajectory. And Newton basically said the planet will continue in a straight line if not for an impulse that alters the direction of the trajectory. And which direction is that impulse? It's in the direction of the sun. So Newton modeled the sun as applying an impulse every tick of the clock, kind of like a computer, and argued then that the triangles must have equal area, establishing Kepler's second law at this discrete level. Here's a little reconstruction of Newton's proof. It requires only high school geometry. Here's just 2 steps of time. The planet starts here. At the next step of time, it goes here. If it would continue under inertial motion, it would end up at position T. But it doesn't continue under inertial motion. It's affected by the pull here towards the sun. So it ends up in position R. So what's the deviation? Well, the deviation has to be parallel to OQ, right? So TR has to be parallel to OQ. And the argument now is that the green and the blue triangles have the same area. And how does this argument work? Well, you start with the red triangle, and you argue that if you just had the inertial motion, you are translating the base of the triangle along the base. So you don't change the height of the triangle, and you don't change the width of the base. So you have the same area. And now, for the second part, you argue that since RT is parallel to OQ, you're now moving the tip of the triangle parallel to the base. So again, you don't change the height of the triangle. So you've never changed the area of the triangle. Very, very simple proof that Newton had. Now, because it's an inherently discrete proof with these triangles and fixed size time steps, we can reinterpret Newton's proof as a prescription for a computer algorithm that advances a system forward in time. Here's the algorithm. All I've done is relabel the diagram. N, the subscript N denotes the time step. Q denotes the position or the configuration of the system. And P denotes the momentum or the velocity. Well, I'm using those interchangeably. I'm just setting mass equal to 1. And H denotes the time step. So if I start at position Q, I can move 1 step in time to Qn plus 1, and I can write down that law at the top left. Qn plus 1 is Qn plus the elapsed time times the velocity. Very simple. What about the velocity update? I can read that from that deviation up there, right? The change in velocity between the first time step and the second is that deviation up there. And so I can write it right down there. And if I look at this law, it looks a little bit like the first law that we teach in integration of ODEs, explicit Euler algorithm. You update the position based on the velocity, and you update the velocity based on evaluation of the force. The way it differs from explicit Euler, here's explicit Euler on the left. Here's the algorithm we got from Kepler's second law on the right. The only way they differ is where the force is evaluated. In explicit Euler, I update my position based on the old velocity, and then I update the velocity based on evaluation of the force at the old position. Whereas in the Kepler second law, or the symplectic Euler formulation, I again update the position based on the old velocity, but I update the velocity based on the new position. And you say, oh, I don't like this, because if I have to update the velocity based on the new position, this looks like an implicit system. I have to stick it into a linear solver as opposed to just evaluating it. But actually, no, if you really look at this, they're both explicit. Everything on the right-hand side here depends on n. So everything on the right-hand side is known. I can just plug and chug to get the answer on the left-hand side. And actually the same thing is true here, because once I evaluate the first line, where everything on the right-hand side is in terms of n, I have Qn plus 1. And so when I evaluate the second line, I know everything on the right-hand side. So in terms of computational cost, neither of them needs a linear solver or a nonlinear solver. They're both explicit equations. But they perform very differently. On the left, I'm computing, well, I'm not computing. This is from a textbook, Lubick and Warner and Hare, a computation of planetary motion with very tiny time steps, 0.0005. And as we can see, over time, this kind of blows up. And this is a well-known attribute of explicit Eulers. You run it long enough, and the planet goes off to Alpha Centauri. That's just how it is. With symplectic Euler, on the other hand, you can run at time steps 100 times bigger, and you retain a qualitatively elliptic trajectory. Now, is it perfectly accurate? No. The accurate solution is this dotted line here. It still deviates from that. But qualitatively, even for large time steps, it doesn't blow up, and it maintains the kind of trajectory we expect to see. So we want to take these kind of ideas, we want to be inspired by building the geometry into the algorithms and apply them also to the spatial domain, to problems using elasticity, liquids, surfaces, and so forth. And most of the systems that we're interested in, most physical systems, are naturally described in terms of differential geometry. It's, in some sense, the mother language for mechanics. Except we're working on the computer, so just like we discretized planetary motion into time steps, we're going to have to discretize our surfaces or curves as samples. And now we're going to ask, how do we rebuild up a differential geometry for these sample geometries? And that's the question. So let's go through an exercise to illustrate what I mean by that. Let's talk about curves on the plane. And let's give the curves an orientation by this arrow. So one thing we can talk about for smooth curves, of course, is their curvature. At any point P, we can fit the best circle, look at the inverse of the radius, and that gives us our curvature, and we can give that curvature a sign. Since we have a direction of traversal for the curve, we can talk about a positive or a negative curvature, depending on which way we're turning. We can talk about the Gauss map for the curve. So for any point on the curve, we have a normal vector. We can take the unit normal and translate it to the origin. So the tip of the normal now falls somewhere on the unit circle or the unit sphere in 3D. And so now, as we traverse the curve, we can consider the image of the Gauss map. And here are some examples of that. If we have a curve that goes in a straight line, the normal always points in the same direction. So the image is a single point on the unit circle. If we have a curve that turns sharply, the unit normal will spend a long time here. Then around here, it will make a rapid transition and then spend a long time here. So it doesn't go uniformly on the unit circle. So we can have all of these natural quantities in the smooth setting that we might be interested in. And these quantities might be related in interesting ways. For example, we can talk about more of a kind of topological property, the turning number, which basically says for any closed curve, if you look at the image on the Gauss map, how many complete cycles do you have on the Gauss map, taking into account sign? And here I've shown you the integer number of complete cycles. So if its curve is closed and the curve is smooth, then the normals are continuous. And then you would expect to always have exactly an integer number of complete cycles. So you can relate these local quantities like curvature and these kind of more global topological quantities like the integer turning number by theorems. And for surfaces, we have the Gauss-Bonnet theorem. For curves, we have a turning number theorem, which says that the integral over a closed curve of the signed curvature is always an integer multiple of 2 pi, right? And here is the integral for these curves here. And this is really interesting because it means if I wiggle around the curve a little bit, I will change the local curvature, but I somehow don't change the integral of curvature. So there's a connection between the topology and the geometry. And so I must have these discrete jumps, these quantum jumps in the integral, and those occur when the curve becomes irregular. For example, when I create a cusp as I transition from one of these curves to another. So this is an interesting sort of construction. We've looked at plane curves. We've identified some interesting differential geometry objects for these plane curves. We've identified some structure that relates these objects. In this case, a relationship between a local quantity and a global quantity. And we might want to have this for a discrete system. So let's look at discrete curves. So here we'll define discrete curves as a bunch of points connected by straight lines. And there are many ways you could think of defining curvature here. We can't just literally take the definition from the smooth setting, because how do you fit a circle? Here you get a circle of infinite radius, and here you cannot exactly fit a circle. So we need to invent some other sort of definition. And there are a lot of definitions that have been proposed. You know, Helmut spoke earlier today about a topic that's closely related and that also involves formulation of different quantities such as this. Here is one choice that is appropriate when you care about the turning number theorem. We say that if we're driving along the curve and we have a sense of direction, then whenever we hit a vertex, we turn by a finite angle, and we give that finite angle a sign. And so we say that the total signed curvature of the curve is just the total of all these exterior angles, or all these turning angles, with a sign. What about the Gauss map? Well, we can take any edge. We have the normal vector for that edge. So that edge maps to a well-defined point on the unit circle corresponding to that normal vector. And what about the vertex? Well, the vertex corresponds to a transition from one normal vector to another. So the vertex maps to an arc on the unit circle. So we have this nice duality, a primal dual sort of structure, where we have edges mapping to points and points mapping to edges on this dual structure. But what remains is that if we have a closed discrete curve, then we will have an integer number of turns in the image of the Gauss map. So we can write down a discrete turning number theorem, which says that the sum of these turning angles for a discrete curve is an integer multiple of 2 pi, namely the 2 pi times the turning number. In fact, the proof in the discrete setting is much easier than the proof in the smooth setting. In fact, we've learned the proof in high school, at least for a simple case. The sum of the exterior angles of a polygon is 2 pi, right? And so you can generalize this proof. So it's a nice instance, again, just like Newton found it easier to prove Kepler's second law in a discrete way. Here we find it easier to prove the turning number theorem in the discrete system. Now, what we've done here is we've taken a smooth picture in terms of differential geometry, and we've built up from the ground up a discrete picture in terms of differential geometry. For that, we've had to define some new objects, such as discrete curvatures. But what is important to observe here, and what I think is really has to sink in, is that there are a lot of ways of taking continuous systems and discretizing them for computation. For example, the finite element method. By and large, the techniques that people have focused on focus on convergence. They ask, what is the rate of approximation error as a function of resolution, right? Can we argue that the error in the discretization vanishes quadratically with the mesh resolution? This is a different philosophy. Notice that it does not matter how coarse the discrete curve is. It does not matter how few the vertices of the discrete curve. The turning number theorem will hold exactly without error. So it's a discrete analog of this structure that exists in the smooth setting. And so that's helpful when you're trying to model a system qualitatively, I think. So that's the basic philosophy. I want to turn kind of from a more detailed kind of mathematical look at things to a little bit of a higher level look at a few applications. And then we will dive back into some math in a different domain if we have time. So, what have we done with this kind of approach? Well, let's look at curves first. Differential geometry, you can think of it as the study of curves and surfaces. We'll look at curves, and then if there's time, we'll look at surfaces. Curves appear in physics at lots of different scales. You have the strands of DNA, you have the flagella of a bacterium, you have the tendrils of a plant, you have old-style telephone cords, you have hair, you have undersea cables, so lots of different scales. One thing that ties all of these kind of curves together is that regardless of the scale, they can be modeled nicely by the theory of Kirchhoff elastic rods, which we won't talk about in full detail. But we'll go back to Mark's frames, right? So Mark talked about frames earlier today, and we'll say that if we have a curve, I'm going to try to repeat his, he did it too well for me. All right, I'll take a cable instead. If we have a curve, it is not sufficient if we have a cable to only model the position of the curve, because it does not distinguish between this configuration and this configuration. The curve is in the same place, but there's more stored energy when I've twisted it. But if for every point on the curve I attach Mark's frames, then I have more information by which I can encode twist. Now I'm going to be a little bit more specific than Mark. I'm going to ask for an orthonormal frame, so I will ask for 3 unit length vectors all mutually perpendicular to each other. So a rotation if you want, attached to each point on the curve. And here's a little animation of this. And so you can see from the way the frame is there, you get a sense that this is a twisted up cable, right? And if the frame didn't behave like, and I like to look at it from first person. I get really dizzy actually on these things, but my friends really enjoy these rides. So, I like to think of it in first person, and you're riding along one of these roller coasters. And so you'll be doing more twisting if the frame is twisting more. And the frame allows you to model these kinds of configurations. This is a simulation now, where there's twisting. And if you can do twisting, you can twist and twist until you get double helices. And you can even get merging of double helices, which has been observed in DNA, the merging of plectonemes. So my biology friends are very impressed with these kinds of simulations because they've said we've never actually seen how plectonemes merge together. But I thought to myself, it just reminds me of this kind of annoying situation. And there's a word for this situation. It's resistentialism. You can look it up. Resistentialism is a theory that inanimate objects, such as a garden hose, are out to get us. They're out to make our life miserable, right? There it is. But in order to do this, I want to tie this back to the geometry. In order to do this, we don't want to just have a frame on the curve. We want to be able to understand how much twist is stored on the curve. And to understand how much twist is stored on the curve, we need to be able to talk about a curve that has the least possible amount of twist. To have the least possible amount of twist, you want to talk about a frame on the curve that is as twist-free as possible. So here's a depiction of that. Let's see if there's an animation. No animation? Here's the animation. There it is. So I want to be able to parallel transport a frame along a curve. And for those who remember the theory of parallel transport of vectors on a smooth curved manifold in Riemannian geometry, it's exactly the same theory. You just have to invoke effectively not the Gauss map, but the tangent indicatrix to map each tangent vector to the surface of the unit sphere. If a tangent vector, which is one of the three frames, is mapped onto the radius of the unit sphere, then the other two vectors, which are perpendicular to the tangent vector, will be lying on the surface of the sphere. And now you are just parallel transporting those vectors on the surface of the sphere. So it's exactly the classical theory of parallel transport prescribes to us how to move frames along here. But if you want intuitively, you're moving the frame as little as possible so that it remains adapted to the curve without twisting. So this is what we had to rebuild up in the discrete domain, was the theory of parallel transport, or natural frames. And here's a little animation of how we did it. But how did we do it again? Again, you can think of it by rebuilding up the theory of parallel transport for discrete curves. I won't go into that now. So once you have this ability to measure twist, you can compute problems of elasticity that include twist. So here's a fun one. You take a slinky, a helix, and you stretch it out, and as you bring your hands together, you get two helices of opposite chirality, and that's the simulation at the top. And what's frustrating about these helices of opposite chirality is that this is actually a local minimum of the energy. It's a stable configuration. If you don't believe me, here it is. Right? It's also on plants. Here's an example on plants, right? So there's applications of a system that can model this. There's applications of different things. One of the first ones we ran into was the guys at Adobe wanted to do paint brushes for Photoshop. So since Photoshop 5.5, there's physics-based paint brushes where each of the bristles is one of these elastic rods. And because you can get qualitatively correct behavior with very low resolution, they can run this in real time. They also put GPU acceleration and so forth, but the key point is you can run it with very few vertices and get the right behavior. Other researchers have used this to model flexible needles in the context of medical simulation. So it used to be that if a doctor wanted to deposit a little radiation pellet next to a tumor, they would use a straight, hard needle. So they'd look at an X-ray, they'd look at you, they'd hope for the best, and they'd go in and out and hope they don't hit any vital organs. And as imaging technology improved, they could see a little bit with ultrasound what's going on while they worked. And as materials improved, they realized that they could use a flexible needle where the tip of the needle has an angle. And because the tip of the needle has an angle, as you insert it, it's always turning in the direction of the angle. So how do you control which way it turns? Well, you twist on the outside of the body. When you twist, the whole needle twists. So the tip twists, and so you control and you're steering which way it goes. So now you can imagine the doctor having to twist here and figure out what's going on. This requires some training. So researchers have been working on training tools. Now, once you can model a flexible needle doing this, you don't even need the doctor. You can have robots control the needle with a flight plan set by the doctor. But again, you need a physical model first for what's going on. As Ayelet said, some of the film studios were interested in this. Here's some of the animations they were doing with it. Also, some condensed matter physicists at MIT who have since become nice collaborators of ours. We did a PNAS paper with them recently, studying their experiments side by side with simulations. Here is all of the transoceanic cables that have been put down for internet and communication since the World War. And they're put down by a ship. And the ship basically has a cable that's coiled up and is deposited as the ship moves along. And if the ship moves too fast and deposits the cable too slow, the cable can snap. If the ship moves too slowly, the cable can tangle up, and that causes other problems and is also wasteful. So the question is, at what speed should the ship go to kind of deposit a kind of slight sinusoidal pattern that has enough give, enough slack in case the plates shift, for example. So this is one of the problems that we studied in this paper. Since then, we worked with them on propulsion of bacteria with flagella. This was published in Physics Review Letters. Again, using experimental techniques side by side with these simulations that were intended for qualitative purposes, but have turned out to be quite accurate in terms of matching experiments. Now, I want to slowly start shifting gears from elastica to fluids for the remainder of the talk. 5 minutes left? Really? Okay. So I probably will only have, let's see if I skip. I'm going to skip to this other question here. So this is some late-breaking stuff that my student Fang Da is publishing this year at SIGGRAPH. And here is a droplet falling and splashing. Looks pretty nice. We've seen a lot of fluid simulations before. They're all over. But the question here is, except for Srinivas, can the rest of us see beneath the surface of the liquid, right? And in general, when we're looking at these animations, what we're really seeing is the surface of the liquid. And so I'm really switching here from discrete differential geometry or differential geometry as the study of curves to the study of surfaces. And I'm asking, can we just model the fluid not by putting variables everywhere in the volume, and of course the fluid, the liquid, is a volumetric phenomena, but can we model it just by putting variables on the surface? So really just as a triangle mesh, if you want, just mesh processing. That's the question we were asking ourselves. To do this, of course, we're going to need a lot of classical mesh processing techniques. You have a triangle mesh that describes the liquid, and you have to do all of the typical mesh operations to track the frontier of the liquid. So if you have merging droplets, you'll have to do all the usual mesh processing. But I want to talk here about the physics and kind of what geometric insight do you need about the physics in order to make a transformation that allows you to really capture the physics just by looking at variables on the triangle mesh. So here I've written down in the simplest possible form I could, essentially the Navier-Stokes equations for a fluid where we are neglecting viscosity, so the incompressible Euler equations. The top equation is just F equals ma. It's just Newton's second law. The left side is just acceleration, and the right side is just the forces acting on the system. And the bottom part is an additional constraint, which says that U, which is a vector field over all of 3D, that describe, or over all of the liquid, that describes the velocity of the liquid is divergence-free, meaning you can't build up more and more liquid in one spot. This liquid is incompressible. It's not like air, which I can squeeze into a cylinder, into a pipe to carry around. It's like water, which is very hard to compress. So that's what we need to know out of this, is that we have a velocity field u, and it's divergence-free. So here's my velocity field u for some droplet on the left. And here's what I want to have. I want to have a representation only on the surface. And ideally, I don't want to lose any data. I don't want to cheat, ideally. So if I don't want to cheat, I basically have to go back and forth between these two representations. If I can't go back and forth, I'm probably cheating in some way. I'm losing some information. So really the question here is a geometry question, which is, can I set up a bijection between data living only on the surface, only on the boundary surface, and a vector field only on the interior? Is there such a bijection? And so, you know, in general, if you have an arbitrary velocity field, I think it's pretty intuitive that it's hard to reduce it to just data on the boundary. Because you could have any terrible thing going on the inside, and you won't see it on the boundary. But maybe the fact that the liquid is incompressible is enough to save us, to reduce the space of vector fields we're interested in. But no, it's not. Here are two vector fields that are both divergence-free, and they both have exactly the same restriction onto the red circle. But very different things going on the interior. So it's not enough that it's divergence-free, unfortunately. But if we think for a second of divergence of a vector field as a one form, and we think of divergence-free as a closed one form, what if it was co-closed? What if it was also curl-free? Then we can turn to Poincaré for some help. So if we have a contractible domain, and we have a co-closed one form, or a curl-free field, then that vector field can be written as the gradient of a scalar function. And that scalar function turns out to be a special scalar function if the vector field is also divergence-free. In that case, it's a harmonic function, solution of Laplace's equation. And that's nice. That gets me very happy, because if I have a harmonic function, I immediately think of uniqueness of solution to Laplace's equation, and if I think of uniqueness, I start to have a plan for bijection. So if I have a vector field u, and I know that the vector field is both divergence-free and curl-free, then I can write u as just the gradient of some scalar function that's harmonic. I take its restriction onto the boundary, and that's my data, a scalar function over the boundary surface. And how do I recover the original vector field? Well, if I know that I'm looking for a harmonic function, I just solve Laplace's equation subject to Dirichlet boundary conditions, and then I take the gradient, and I get the vector field. So the only question is the assumption that the field is curl-free legitimate? And I will briefly answer that by saying, yes, the geometry told us to ask for a curl-free vector field. And it turns out that you can argue from physical principles that it's legitimate if the fluid is inviscid. I won't have time to convince you of that now. So here's simulations that are being run on a triangle mesh. All the variables are living on the surface only with these scalar functions, reproducing the kind of phenomena that we've seen for volumetric fluid simulations. And while I play these, I will leave a minute for questions, or no minutes for questions. All right, thank you very much.